Hello, experimenters. I'm Seth Noir, man behind the camera with the exceptional handwriting you just seen a laugh. This is my favorite experiment. I like this one. I like this one because we're going to find a universal constant, the magnetic permeability of free space. mu0, which equals exactly 4 pi times 10 to the minus 7 newtons over amp squared. The way we'll be dealing with it is we'll look at mu0 over 4 pi, which equals 1 times 10 to the minus 7. All right, so here are some examples of where this occurs in physics. It occurs in the law of Biot-Savart. Also in Ampere's law. And that, along with another constant, epsilon naught, is how we can calculate the speed of an electromagnetic wave in a vacuum. That's right. We're going to be finding one of the 2 constants needed to find the speed of light. Yeah. Okay. All right, so let's make sure we're all on the same page here with our coordinate system. The x direction will be this way. For the theory part of this, all of our currents will be in the x directions. The y direction will be up and down, and then the z directions will be in and out of the board. All right, so now, this is all about current carrying wires. We need to determine the magnetic field, and the direction of the magnetic field in a current carrying wire is determined by the right-hand rule. We take our thumb and we point it in the direction of the current, and then our fingers curl in the direction of the magnetic field around the wire. So the magnetic field is going this way around that wire. All right, so this is one way to picture it. There's another way to look at this. In other words, these dots here represent arrows that are coming out of the board. It's like you're looking at the tips of the arrows coming at you. And then the crosses here represents the vectors going into the board. It's like you're looking at the tail feather of arrows. And this representation is what I'm going to use for the rest of this. All right, so with a little Ampere law action, we can determine the expression for the magnetic field. All right, so we find this expression here for the magnetic field, mu0 over 2 pi times the current divided by r, and that's the distance from the center of the rod, just some distance away. All right, so the force produced by the magnetic field is determined by the cross product of IL cross B. Everywhere the magnetic field is perpendicular to the current. So it's just ILB. And then substitution. Substitute that B in for this, and then we find an expression for the magnetic force. mu0 over 2 pi Li squared over R. All right. Okay. All right. So what we're interested in is 2 wires. 2 wires that are in an equilibrium position. All right, so let's just label this up. All right, so the R will be the distance from the center to center of the wires. All right. L will be the length of the wire. And I want you to note that the bottom wire is always fixed in place. The only wire that will be moving is the top wire. Okay, so we want to disturb this equilibrium position. And to do that, we'll put a mass on the top wire, and it'll push that top wire down. So if we want to return these back to the equilibrium position, we got to find a way to put a force going in the opposite direction. And we'll do that with a magnetic force. We're going to put a current from this bottom wire here. All right? So that's going to give us a magnetic field curling this way, so it'll be going out of the board here. And then in the other direction, we're going to put a current going the other way. And this will interact with this magnetic field and it'll produce a magnetic force. All right, so once again, the force is I L cross B. So we need a right-hand rule again, but a different variety of the right-hand rule. Our index finger needs to be in the direction of the current. Middle finger is going to be in the direction of the magnetic field. And then our thumb will give us the direction of this force. We need it to be up. Let's just make sure it's going up. So, index finger in the direction of this current. Magnetic field coming out of the board. That's my middle finger. My thumb is pointing straight up. That's the magnetic force. Excellent. Excellent. So, that's the weight. And then straight up. The force from the magnetic field. Alright, so when it's back in equilibrium, we have this expression here. Alright, the two vectors added together must equal 0 because it's in equilibrium. Switching out of vectors, these components are in opposite directions. This one's going up, that one's going down, with the minus sign. Substituting in that expression for force we found before, and then solving for the weight. All right, are we done? It seems that we are, because look. Well, if I could put a series of different masses, and then for each mass find the current to restore that equilibrium, I could find the line, so I'll have the weight versus the current squared, a linear equation, and then this would be the slope. And if I could find L and R, I could find the magnetic permeability of free space. I wish it was that simple, but it's not.